In the next set of videos, we will discuss the all-important notion of completeness. Recall that a metric space X is said to be complete if any Cauchy sequence converges to a point in the metric space. The most important result in this section would be Baire's category theorem, and also a fact that any metric space can be completed. In fact, any metric space can be isometrically embedded within a Banach space. That I will leave it to you as an exercise to prove in a long chain of simple problems that will finally end with the result. I will sketch a proof of the fact that any normed vector space can be put inside a Banach space. So let us begin with some simple consequences of completeness. So we begin with a simple proposition. The proof is rather easy. Proposition: any closed subset of a complete metric space is complete, and vice versa. That is, any subset of a complete metric space which is also complete is going to be a closed set. Okay, and vice versa. Or rather, I could have stated it like this: a subspace of a complete metric space is complete if and only if it is closed. Okay, so proof. Let's begin with the proof. Suppose F subset of X is closed. Let Xn in F be a Cauchy sequence. Then Xn converges to X in X because X is complete. But F is closed, and therefore X is an element of F. Okay. Now on the other hand, suppose F is closed. That's the case that we did with. Suppose F is complete. And X is an adherent point of F. We have to show that X is in F, but that's obvious because we have a sequence Xn that converges to X. That's the definition of an adherent point, and this Xn is a Cauchy sequence. Right? So by completeness, the limit of Xn should also be in F, so X is in F. So a closed subset of a complete metric space is complete if and only if a subset of a complete metric space is complete if and only if it is closed. Okay, now what we do is we generalize Cantor's intersection theorem to metric spaces, and again completeness will play a role, and that will become very clear during the course of the proof. I am going to prove the version that's most useful in applications, the version where you have the intersection to be a single point. Okay, let X be a complete metric space, and let Fn be nested, closed, non-empty sets. Okay, so what you do is you consider nested closed sets that are non-empty with diameter of Fn converging to 0. So this is essentially the shrinking case of the Cantor's intersection theorem. Then F, which is by definition equal to intersection of Fn, is exactly, I should not write not equal to, is a single point. It's a singleton set. So the intersection of closed non-empty shrinking sets in a complete metric space is going to be a singleton set. And the proof is again rather easy because we have already seen proofs of several versions of this Cantor's intersection theorem. The metric space situation poses no additional difficulty. Now the fact that diameter Fn converges to 0 clearly shows that the intersection cannot have more than one point. That's obvious. The intersection cannot have more than one point. Now all that needs to be shown is the intersection is non-empty. Okay. Now what you do is the following: choose xn in Fn. Okay. It is clear that this xn is a Cauchy sequence. It is clear that xn is a Cauchy sequence. Okay. And because we are in a complete metric space, xn must converge to x in X. But each Fn is a closed set, and therefore this x must be an element of Fn. So this x must be an element of Fn by closeness. And of course this is a rather easy argument that we have seen before. You just ignore the first few terms of the sequence, then the rest of the sequence will be contained in Fn. Therefore the limit x should also be contained in Fn. Okay. Thus intersection of Fn is nothing but this singleton set X. This proof was rather easy and is modeled on the proofs of Cantor's intersection theorem that we have seen earlier. Okay. Now the next order of business in this line of generalizing facts that we have already seen in the context of real numbers to metric spaces by essentially doing the same argument, replacing the absolute value by the metric D, is Baire's category theorem. Okay. So for that we need a definition. And the definition is that of a nowhere dense set, which we have already studied. A subset S of a metric space X is said to be nowhere dense if interior of S closure is the empty set. Okay. Now I am going to leave a very simple exercise for you. I am not even going to bother calling it an exercise because it's rather easy to show. Remark: suppose S is nowhere dense. Or rather, let me phrase it as an if and only if condition. S is nowhere dense if and only if each non-empty subset of X, each non-empty subset of X has a non-empty, each non-empty open subset, sorry about that, each non-empty open subset of X has a non-empty open subset that does not intersect S. Okay. Please prove this exercise. Please prove the content of this remark as an exercise. This is rather easy to see. Set S is nowhere dense if and only if, no matter what non-empty open subset of X you take, you can find an even smaller non-empty open set that does not intersect S. Okay. Now we are going to state and prove the Baire category theorem. Baire category. What Baire category theorem says is the following. A complete metric space cannot be written has as a countable union of nowhere dense sets. So you cannot write a complete metric space as a countable union of nowhere dense sets. On to the proof, the statement might look somewhat sophisticated compared to the statement of Baire category theorem that we saw earlier in the context of the real numbers, but the proof is so short and the proof is so similar to what we have seen in the context of the real numbers, that you will have no difficulty in understanding what's going on. So let an be a countable collection of nowhere dense sets. Now the aim is to show that we can find a point x in the metric space which is not there in the union an. So what we are going to do is this: let b1 be some ball of radius 1. Any ball, it doesn't really matter, just choose some ball of radius less than 1 with the key property that b1 is disjoint from a1. Why can you find a ball of radius less than 1 that is disjoint from a1? Well, you have to solve this remark. This content of the remark precisely says this: a set is nowhere dense if and only for each non-empty subset we can find an even smaller open subset that does not intersect S. The moment you solve this exercise, this will be clear to you that you can find a ball of radius less than 1 that is disjoint from A1. Okay. Now what you do is let F1 be a closed ball concentric to B1 of radius less than half. Concentric just means that this F1 has the same center as B1. Okay. Now we can find, again inductively, we can find B2, some non-empty open ball in F1 such that B2 intersect A2 is empty. Again, this just uses the fact that A2 is a nowhere dense set and F1, or at least the interior of Fn is an open set. Therefore, we can find some possibly smaller ball that does not intersect A2. Okay. Now the argument should be rather clear. Choose F2 to be a concentric closed ball to B2 of radius less than 1 by 4. Now choose B3. Choose B3 to be contained in F2 some ball such that B3 intersect A3 is empty. Rinse and repeat. Repeat this argument. We get a sequence of non-empty nested closed sets. Okay. By Cantor's intersection theorem, this intersection of all these Fn's is going to be non-empty. The intersection of all the Fn's is going to be non-empty. Of course, we have used the fact that diameter of Fn is going to converge to 0. That is clear by construction. Okay. Now this point x, which is exactly the intersection, is going to be in each Bn. Okay, that means X cannot be in the union. X cannot be in the union of ANs. It cannot be in any AN, in fact. Okay, so this proves Baire's category theorem in the context of metric spaces. Now, I'm not going to give any applications of Baire's category theorem in this course, but it is extensively used in many places, including functional analysis, and you will no doubt come across such applications in your future studies. This is a course on real analysis, and you've just watched the video on completeness.